this is partly to force me to write better documentation. Doing this is linked to working out how to write the documentation. I've written a open source FPGA, and I thought I'd be along good company in the open cause movement. I discovered that no one else has written an open source FPGA, so I don't have anyone to copy or anything. I've tried it on my business, done mumbling. First thing, what is an FPGA? In the finest traditions of acronyms, it doesn't sound like what it is. It's a field programmable gate array. It's because it's not programmable, not done in the field really, doesn't involve any gates and is only vaguely an array. It's better described as reconfigurable logic. I'll just see if I can start to guess and see if I can get my pointer. Yes, pointer still work good. This breadboard, in contrast with the traditional way of prototyping circuits before you burn a PCB or whatnot, you have a breadboard which has various predefined strips here and a power rail here, and this mouse is tremendous, it's better than nothing. You plug your components into the strips and it makes a circuit, and that's all well and good for testing things. And FPGA is the opposite, where you have your component. I can't reach over there, right? You have your predefined logic blocks, which can redefine themselves, think of them as gates or counters or whatever in there. And the interconnect itself is flexible, so you can define that via your computer plugged into it to monitor what's going on, and you can digitally redefine the interconnect. And the FPGA is all inside a silicon chip, so redefine the interconnect alters lots of little switches, memory elements connected to switches, and you can prototype digital circuits up to a computer and everything there. It's important to put it into context. I did have a better slide here, but I managed to overwrite it because I was in a hurry. Putting it into context of the mystery box, which turns your code into doing something useful. I'll just skip ahead here to see what. Oh yes, right, yeah. It's contrasting the clunky way a computer works with a kind of flowchart that you'd use in your program, but an FPGA kind of works like the flowchart in the first place. It's kind of physical arrangement of the box and flowchart. And it follows a little animation here, where you have on the left side here you're represented. Where's it coming from? Right, no, it's. Is that there or not? No, there it is. Right. I would try my alternative mouse, but I don't want to drag on into the pub. Your program here, your instruction register, it just stores the representation of instruction register, program counter moving, and the data to be manipulated, and the other fun bits of the processor which do stuff. And down here, you're kind of like your program flowchart, but at the end, it will run in an electronic way. Right, so I'll switch to the top, and you can see the very clunky way in which so-called modern computers spend most of their time shoveling data around rather than doing anything with it. And it's all the worse with the slow speed of memory and the fast speed of processors and multiple caches and all that kind of thing. So it's taking about 40 steps or so to add two numbers and then multiply them together. And coming up to the end, this will the off switch there will switch on, and it will flow through in less than a clock cycle, so that the FPGA way is better. There's a joke there with deep thought and the Hitchhiker's Guide to the Galaxy stuff. Right, so the traditional structure of FPGAs is you have these little squares called configurable logic blocks, which are the components you need to connect, and the grid of an interconnect, which is the bit that connects and which I referred to earlier. And the detail of that is at the junctions of the interconnect, you have this complex little switching circuits, which route things around, and coming off the complex logic blocks as inputs and outputs, they plug in where they need to on the interconnect. And so it splits into the complex logic blocks and the interconnect, and those are the two things I've changed in my design, which are all a bit, that's a bit useless. I'll come back to that. Firstly, the grid, I've gone with a fractal grid instead, because mathematical principle called Rank's rule means that the square grid has too much redundancy, too much unused bits in it. Most of what you want to connect is like modular, and then you connect other modules, made up of modules, and so forth. And you really only need a fractal interconnection. Rank's rule will tell me how much of each I need. So it goes from the equivalent of complex logic block here, into several of them into one level of interconnect, and then that level of interconnect goes into a bigger interconnect, and eventually the end level interconnect goes off to the inputs and outputs to the chip, and which just lead into the outside world. And I've also added inputs and outputs which are readable as memory locations, so it can self-modify what it's doing. Let's see, there's that. This is the traditional configurable logic block, which looks like a complete mess to me. Sometimes called the complex logic block, and they're not kidding. Instead of just having a lookup table, like a kind of universal gate, a bit like a fast memory, and you have several binary inputs coming in and one binary output, and they bind in flip-flop unnecessarily into more complex logic, but you could actually put that in the loop. So that's an inefficiency, and I think I have this. Do I have the? No, I don't have that. Right. Here's the traditional heart of it, the loop, and down here you have these. You have coming in here simplified a 2-bit binary information, and you need a combination of 16 states, which can be represented by 4 memory cells coming in there, and that can define any 2-input gate, which unfortunately this only provides one output, and that is the traditional design. So my design is to flip this thing around, and that power thing there just turns it into a simple decoder. If you define memory cells within your loop, and you might want to clear them, then you just switch that off and on, and it clears it, which is the necessary feature if you do that. You can define follow on the memory cells, which if say both these inputs are on, it will output along this line, and this configuration here represents an AND gate, so it will only fire off this output if it's like an AND gate. This one for an OR gate, this one for a NAND gate. So you can have you have as many outputs as you like there, and using the traditional one, you'd have to have one loop for each output, and so it's a bit more compact there. This is a sort of demo showing. So I'd like to show what's going on inside things. This is the demultiplex. I always get those two mixed up. They're the same thing. and it depends. They call them a demultiplexing. If you connect it the other way around, but it's exactly the same circuit. And sometimes you call it a decoder. Once again, the same circuit. So you've got these two inputs coming in, and with representing the number 0 at the moment, and line 0 is connected there, and that triggers off these three lines which represent 0 on the 7-segment display. So that's both adding up the numbers of inputs and producing an output and compressing quite a lot of logic into one place. I can run that across there, and each time it produces the output. So that's like compressing a truth table, if you know what that is, which I should have defined before, but into easy block. So you don't need the flip-flop there, because you can form a flip-flop yourself by feeding the output back into the input. And this is a slightly more ambitious one. It's not going to run through all 16, because I didn't have the patience to define that. This has your 4-bit input representing 16 possible states. A little decoder there running into this thing, which will show from 0 to F, or it would if I defined all of them. So I'm just going to run through a few there. Normally you would not have 7 outputs coming off one loop, a maximum of 4 really, so you'd use 2 of these inside your chip, because most applications do not require 7 outputs. Right, what have I got next? Yes, and beyond the simple stuff, some FPGAs have what they call block RAM, which is definitely internal RAM for internal fast RAM. You can define that within the loop, but it wastes space. And I decided to, because there's spare memory in the configuration memory which defines what the loops do, I've decided to reuse that so that above the line it's accessed as block RAM, and below the line it's accessed as normal reconfigurable stuff. So you can make more efficient use of the chip. I haven't animated moving the partition to the exit point. And this is to remind me to talk about stuff of flipping the multiplexer thing around. I've already done that. RAM start access. Yes, the JTAG access for FPGAs comes from when chips were much more expensive and there was a much smaller area, so they use the kind of shifting information into it and out of it, which is a bit crazy, because that carries on today, even though we have plenty of chip area to play with, and the logic is tremendously fast. It's using a slow method to access a fast chip, and that seems a little crazy to me. So I'm going to implement traditional RAM style access here, so you can specify what you want to look at and just go directly to it. But I'll keep the JTAG for backwards compatibility. And that internal I/O, yeah, I've already mentioned internal I/O. I just threw this together very quickly, as you can tell. Memory protection is important, because with self modification, one application of that is you might have some kind of, where you normally have a host machine external to it, you could perform much of the functions of the host machine inside part of the FPGA, and then you modify another part of it with the first part. You need memory protection so you don't accidentally overwrite the thing that you're doing the modification with. That's possible. I don't want to run into hard type now. Some applications of reconfigurable logic is when you have a block of it as part of a processor, and you might want it to say decode JPEGs. Another time you might want it to do encode video or something. But if you reconfigured it in the middle using your computer, it would defeat the object of speeding things up because it takes so long to write that extra code into it. So I'm having banked memory so you can have alternate configurations for the same one and select which one you want, and then that should make that easier or practical. And my only concession to quantum computing, the only thing useful I found quantum computing for is generating practically unpredictable random numbers. Via a thing called avalanche breakdown, you can do that. I haven't included the circuit diagram here because it is weird. But it is valuable to have a hardware random number generator for such markets as cryptography and some types of AI. So I'm trying to add in what users will want. The traditional FPGAs, because they hide how they work, they have a lot of software bloat on the computer used to configure it. And it's partly to keep things secret and partly to, partly because they're sound an expensive thing and they want to offer lots of tools. But if my open source thing, it will not only be possible to access the detail of it directly because you'll know what the detail is. Otherwise, it's like trying to use the electronic breadboard blindfolded. You wouldn't do that. So you should simplify it, and you should be able to get smaller amounts of software and a less expensive PC to operate it. I had to upgrade to a much more expensive PC to start using FPGAs. What else here? JTAG data. These are all the internal things which are fun to have inside it. Most of which are standard. I'll skip that to compress time. And here's some humour at the end. The preceding situation of before there were FPGAs, people just had lookup tables in a chip, and they made them quite large, 20 inputs, 20 input and output lines, which led to about 1 million decode lines, which is as much as they could stuff into a chip. And the very smallest FPGA at the moment has 64 4-input loops. So that gives a maximum number of input-output lines of 256. And someone asked me the other day, why don't you just have a giant loop? How many decode lines would 2 to the power of 256 be? And that's just what I just said. And it turns out to be that, which is a lot larger than I was expecting. In fact, that's an error, and the real number is much bigger. But there's nothing to compare a ridiculously large. That at least you can compare to things in this universe. The true number, the entire universe would be smaller than a pixel to anything you compare it to. So that's not going to work. So we'll go with this one. That is the size of the chip that would have to be compared to the known universe, and that's clearly impractical. But there is so that explains why they stopped using single loops and they went to the more advanced design, which is much more efficient. That is just a very large 2D grid. How big would a 3D grid be? Is that more practical? Well, not exactly, because that's clear. It would take millions of years to construct that, and probably about 40,000. That's about, I think it's 10,000 light years across. So just due to the light speed barrier, that's impractical. And anyway, it would go gravitational collapse and become a black hole before you you run a calculation. Right. So that's it, and that's the importance of getting the maths right before you start designing anything. So, any questions, or just go off down the pub? Right,
So-
okay.
I have a quick question. Are you selling the hardware? You can, like, is there just a preset, like, the open source thing is the specification, the design of it?
Well, I'm making it open source to try and raise standards in the industry because no one else has an open source one. And I think I've thought of a few things that the closed source people haven't thought of, or maybe they have thought of them, and because it's closed source, we don't know. I intend to, at the moment it runs, it's just diagrams on paper, getting the thing refined, and I'm starting to run it as software simulation on a little Raspberry Pi. And after that, I'll run the FPGA design soft loaded onto a traditional FPGA, and then I'll look at things like tiny tape out and try to get try to go into silicon. And I have various things that can run on it, like a kind of AI, although that looks surprisingly powerful, dangerously powerful, in fact. So I'm keeping that closed source because I like to make some profit somewhere. That's the current state of it. Yeah.
How much will a tape out? Tape out is getting the chips made, right?
Yes.
How much would you need to get a batch of chips made? My understanding is it's like
Well,
many
normally
thousands.
millions, but
Yeah.
Tiny Tape Out is this Spanish run outfit where, with the support of Google, they let you do it for $100 plus postage and packing. It's set. Your design lives with 100 other designs in a subdivided chip, and it runs quite slowly. And they say the thing that the ARM and so forth don't tell you is they don't just burn a chip and sell it. It takes dozens, possibly hundreds of iterations to get the thing working. It's much longer to debug it than other things. So it probably costs a few thousand to run through debugs and things. But they let you do it at a reduced cost if you have open source. So this is open source, and that qualifies as a reduced cost, which will save me a lot of hassle. And the profitable stuff is closed source, and that's separate from it.
Looks like we're all done. Thank you very much.
Right. Okay. Thanks.